There's this recurring debate in AI circles that always catches my ear.
Oh, yeah. Which one?
The big one. Is computer vision finally a solved problem? I mean, we see these amazing generative models making videos from thin air,
Right.
but then you hit this wall. If you wanted to do something really complex, like, I don't know, mask every single screw in a 30-minute engine repair video, you were back to square one.
Just tedious manual clicking, one object at a time, a total chore.
Exactly.
And that sticking point, that need for constant human hand-holding is precisely what we're going to get into today. We're looking at a really great analysis from Asmat over on binaryversa.com.
The one titled SAM3, Concept Segmentation and Vision's GPT Moment.
That's the one. It's all about Meta's new segment, Anything Model 3 or SAM3.
So our mission today is to really get under the hood of this thing. Why is everyone calling it the GPT moment for vision? And what does Promptable Concept Segmentation, or PCS, actually mean for you if you're trying to use this stuff?
Well, the foundational shift, and the article really nails this, is that it's a moves beyond just, being more accurate.
Okay.
It's a pivot from a purely visual understanding, just seeing pixels, to a truly semantic understanding. We're getting away from telling the machine where to look and starting to tell it what to look for.
Okay, let's unpack that semantic shift. Why were the older models, SAM1 and SAM2, even though they were powerful, why were they so limited?
They were fundamentally reactive tools. I mean, they were incredible for what they did, but they were basically just translators.
Translators of what?
Of your intent. You had to give it a geometric prompt to click, a box, maybe a rough mask. It needed you to point directly at a single target. It was great at localization, but it couldn't do a conceptual search.
So Promptable Concept Segmentation, PCS, that's the thing that changes this whole interaction. Instead of giving it coordinates, you're just giving it a word.
Precisely. SAM3 flips the entire script. It accepts concepts, natural language, kind of like a search engine. So instead of clicking on one specific car in a photo,
you just type car or red vehicle.
Exactly. Or even something more abstract, like all the tools on the workbench. And the model just goes and finds every single instance of that concept in the image, or, and this is critical, across a whole video.
And the article on binaryversaio.com points out that it's not just one or the other, text or geometry. You can combine them.
That's where the real power is. It creates this synergy. You can give it a text prompt, let's say cat, and then also give it a visual example, like a loose box around just one of the cats.
And from that, it figures out what you mean.
It generalizes from that combination,
right.
Learns what cat means in this specific context, then finds everything else that looks like it. So the task shifts from segment this one thing I clicked on to segment everything like this.
Okay, that sounds amazing, but my skeptic alarm is going off. Historically, when you ask a vision model to find everything based on a concept, you get a flood of false positives. You get hallucinations. If I ask for every circle, it starts masking shadows and light reflections. How did Meta stop this thing from just spitting out garbage?
That was the absolute core engineering problem they had to solve. That's the headache with open vocabulary segmentation. You know that classic example, right?
Yeah.
You ask an older model to find a unicorn in a picture of a kitchen.
Right.
It's so desperate to draw a box that it finds the most unicorn-like thing it can. Maybe it's a white blender or a shiny faucet. And it puts a box around it, even though a unicorn obviously isn't there. It prioritizes finding something over being correct.
And that lack of confidence is a deal breaker in, say, quality control on a factory line or in scientific research. A false positive is wasted time, or worse, a wrong conclusion.
Absolutely. So the breakthrough, which the article details, is this really clever architectural tweak. They rebuilt the whole thing on a shared perception encoder backbone. But the genius move is that they decoupled the process. They split up recognition.
Which is the object even here.
From localization, which is, okay, where is it?
And this is where that global presence token comes into play. It's like the model's built-in skeptic.
That's a perfect way to put it. This presence head's only job is to generate this token that predicts the probability that the concept even exists in the frame at all. All the expensive work, the localization, drawing the pixel masks, that only happens if this token gives a high score.
So if I give it my kitchen photo and prompt unicorn, the presence token looks at the whole scene and just says 0 chance and shuts down the whole process before it even starts.
That is the mechanism.
Yeah.
And it's a huge achievement. It gives the model the ability to confidently say, I'm sure this is not here. That reliability changes everything. It makes concept segmentation usable in the real world for high-stakes work.
Okay, that covers the reliability. Let's get into the hard numbers. How does this generational leap stack up against SAM2 and the other big models out there?
Well, if you're thinking about using SAM3, you're really looking at three massive differences. First is the input modality. SAM2 only got geometry.
Clicks and boxes.
Right. SAM3 gets text, geometry, and image examples.
Yeah.
Second, the output scope. SAM2 was a one-and-done single-target tool. SAM3, with PCS, finds all instances of a concept, exhaustively.
And the third one, video persistence, that's where so many models just fall apart, especially when something goes out of frame for a second.
It was a notorious pain point. SAM3 has this memory-based tracker baked right into the main detector. So if an object like a specific delivery truck gets blocked by a building and comes out the other side,
the model doesn't get confused and think it's a new truck.
Exactly. It re-identifies it.
Yeah.
Older systems would just lose track and create a whole new ID. It was a mess.
Okay, so let's talk benchmarks. To test these new conceptual skills, Meta had to basically invent a new yardstick, right? This SACO dataset.
Yeah, SACO, which is segment anything with concepts. And it is, it's a colossal data set. It's built specifically to stress test this kind of generalization. It has over 207,000 unique concepts.
Now, how does that compare?
For context, that's something like 50 times more concepts than you'd find in most of the classic vision benchmarks. They needed that kind of diversity to see if the model could handle truly random, niche prompts.
And the performance wasn't just a small bump, it was a huge jump.
It's a true step function change. On the classic LVIS dataset, in a zero-shot test, SAM3 hits a mask AP of 48.8. The previous state-of-the-art was 38.5.
And a 10-point jump in AP is massive in computer vision.
It's unheard of. Gaining 1 point can take years. A 10-point jump from a generalized model like this just confirms the architecture is fundamentally better.
And what about on their own, much harder benchmark, SACO? How does it look against models from, say, Google?
It's not even close. It really shows the power of PCS. For image segmentation, SAM3 gets a 53.9% CGF1 score. For comparison, a great system like OWLV2 gets 24.6%. Gemini 2.5 Pro is at 13.0%.
So it's more than doubling the accuracy of the best available systems.
Pretty much.
The article also mentioned its video consistency scores were approaching human level. I'm always a little wary when I hear human-level performance.
And you should be. The numbers are impressive, but context is key. So on the video task, using a metric called PHOTA, humans score around 70.5%. SAM3 gets 58.0%.
So it's very good, but there's still a gap.
A gap, yes. But it's incredibly strong, especially with keeping track of objects through occlusion. The trade-off is always speed. The source notes it can do near real time for maybe 5 objects, but if you try to track a huge crowd, the inference time slows way down.
Okay, that power is clearly a big deal. Let's move to the why you should care part. Where does this capability actually move the needle for real industries?
I think the most transformative one is probably medical imaging. Automated segmentation is the holy grail there. A radiologist could, in theory, prompt the system with subtle lesion or calcification cluster.
And it's great for pre-labeling, right? It does it the first pass.
Exactly. So the difference between staring at a blank scan and having a pretty good mask that you just need to refine, that's a massive workflow improvement.
You go from minutes of painstaking clicking to maybe a few seconds of adjustment.
Absolutely. But the source is careful to add a caveat. For really complex, specific biological structures, like tracing one tiny artery in the brain, SAM3 probably still needs to be fine-tuned on that specific type of data to be truly diagnostic.
And for scientific research, that presence token must have a huge impact. It's about data integrity.
It's invaluable. Imagine you're a marine ecologist and you have terabytes of deep-sea video. You're looking for one rare type of squid.
And the old models would be flagging every weirdly shaped rock.
Right. They'd hallucinate.
Yeah.
The presence token lets the model confidently say nothing here for 99% of that footage. It cuts down false positives and saves researchers an incredible amount of time.
And for the creative world, for VFX, this sounds like the rotoscoping dream finally coming true.
Oh, it completely changes the game. Rotoscoping, drawing masks around, moving people frame by frame is one of the most hated, tedious jobs in post-production.
I can imagine.
Now, an artist can just type main character in the blue jacket and boom, they get a mask for that actor across the whole scene. It just removes so much manual labor.
This all sounds incredible. So let's get down to the practical realities. Can you actually run this thing at home on your own machine? And what are the limitations we really need to know about?
The model itself is surprisingly lean for what it does. It's about 850 million parameters.
So for images?
For still images, yeah, you can run it on a high-end consumer card like an RTX 4090. On professional hardware like an H200, you're looking at like 30 milliseconds an image. Super fast.
But the second you switch to video, the costs start to climb. Tell me about that bottleneck, this idea of masklets.
Video's the tough part because the cost scales linearly with how many objects you're tracking.
Mm-hmm.
Every object gets what's called a masklet. It's a little tracked region that has to be updated every single frame.
So tracking one person is easy. Tracking a crowd of 50 people.
It means the system is managing 50 separate masklets in real time. To do that, you're going to need serious data center hardware. An H200 cluster, most likely.
We also need to be really clear about what SAM3 can't do. The article says it's a pattern matcher, not AGI. What are its biggest blind spots?
Well, it's great at segmenting nouns, things, objects, but it really struggles with logic or spatial relationships.
So it doesn't understand prepositions.
Pretty much. That's the main limitation. Spatial reasoning. If you prompt it, segment the man standing behind the blue car, it often fails. It will find the man and it will find the car, but it can't connect them with the word behind.
And good old-fashioned human ambiguity is still a problem.
Always. If you prompt bat, does that mean the animal or the baseball bat? The model needs context. It does have something called an ambiguity head that tries to predict multiple valid masks, but at the end of the day, the user might still need to step in and clarify.
So despite those limits, it seems like the biggest, maybe the most strategic use for developers is building auto-labeling pipelines.
That's the killer app. That's the real economic game changer. You wouldn't put this huge 850 ember parameter model on a little security camera or a drone.
No, it's too big.
All right. Instead, you use SAM3 in the cloud to auto-label a massive high-quality data set of whatever you care about. Let's say specific types of pests in a field. Then you take those perfect labels.
And train a much smaller, faster model on them, like a YOLO or an RTDTR.
Exactly. Those models are tiny and super fast, perfect for the edge. SAM3 just completely demolishes the biggest bottleneck in AI development, the time and cost of data labeling.
So as we wrap this up, let's go back to that GPT Moment analogy that binaryverse.com used. What does this all really mean?
It's about standardization. Just like GPT made language the standard input for everything from translation to coding, SAM3 is making concepts the standard input for vision. We're finally moving away from models that were just digitalized that needed a human to point them to models that have a cognitive layer, a brain behind the eyes.
And the elegant little piece of engineering that makes it all work is that built-in skepticism, the presence token.
That's the key, that decoupling of recognition and localization. It solves that fundamental problem of models trying to find things that just aren't there. It gives you the confidence score that was always missing.
So the value here isn't just the model's power, but its ability to slash the cost of labeling for almost any visual problem you can think of. If this model can accurately label over 207,000 concepts, what's the next big, expensive visual data set that's about to be democratized? Maybe it's proprietary industrial parts or complex thermal imagery from specialized sensors. The source notes the code is up on GitHub. So now the question for you is, what can you build now that this power